Hi everyone, my name's Matt Gibson Lopez. I'm computer science faculty member at the University of Texas at San Antonio. And today I'd like to give a talk that gives kind of a little bit of a abstracted view of how quantum computers can create advantages that over classical computers, how we can get quantum speed up or quantum advantage, essentially be able to compute the solution to something on a quantum computer faster than we would be able to do it on a classical computer. One of the things for computer scientists, certainly myself, mathematicians, maybe engineers, some folks who haven't had quantum mechanics, is that generally this is taught in a way where it's very physics forward and a lot of quantum mechanics are assume that you already know it, and so oftentimes you may be have to build up some of the intuition behind the quantum mechanics before you would have a chance to understand certain concepts. And at least for me, that was really frustrating that I had to jump through so many hoops before I could even just get a taste of how can quantum computing be advantageous over classical computing in certain settings. So I'm hoping this talk is hoping to be able to kind of abstract away some of the physics, hide a lot of what's going on, make some simplifying assumptions, but to truly be able to communicate the way that quantum computers have the chance to be advantageous in certain situations. So I think after this talk, someone who comes into this with only a classical computing background will truly be able to understand and appreciate some of the ways in which quantum computers and quantum computing can be a little different than classical computing and how you can actually get some advantages. I'm not going to assume any quantum mechanics. I'm not even really going to be assuming linear algebra in this talk, which don't get me wrong. The way we teach it, we assume linear algebra. And in my opinion, trying to go beyond that is not useful. I definitely think if you're serious about learning quantum computing, you're going to need to know linear algebra pretty well, and not just a little bit. Really want to be able to visualize what's going on with the linear algebra. But I think hopefully, my hope with this talk is I can excite people to take on the challenge of learning quantum computing, being willing to persevere through a lot of prerequisites that you have to kind of build up to really be able to get into it. And hopefully, this can be like a spark and some encouragement to persevere and because it really is a kind of an exciting field. Okay, so classical bits and qubits, the basic building blocks of a classical computer, which are the computers that we use today, versus qubits, which are the basic building blocks of the quantum computer. So classical bits can basically be 0 or 1. They're like implemented with a switch. You can think it off means 0 and on means 1. To observe the value, just look at it and you can tell if the switch is on or off. So like if I have a switch in a classical bit right here on my desk and invite somebody to come in here and take a look at the bit, they can just look at the bit and see whether or not the bit's on or off and be able to tell if it's 0 or 1. So it's either 0 or 1, not both. And anybody can just come by and look at it and see what this value is. Qubits, they also have kind of a 0 state and a 1 state. So that they don't necessarily have values the way we think of classical bits of having a value. We use this notation here. This is called this symbol here is a ket. This is physics notation, Dirac notation. This is called a ket. So I might call this ket 0 or ket 1. And these are states that the qubit could be in that are essentially equivalent to the classical bit 0 or 1. But the key difference here is that the qubits can exist in a superposition state in which they're kind of some 0 and some 1 at the same time. right? So we have this ket notation, ket 0, ket 1, and superposition states are states that are a combination of 0 and 1 at the same time. Okay, so I'm going to talk a little bit about the superposition states before we kind of go back to high level qubits. So, in we're going to be considering in this talk kind of four main superposition states. Superpositions in reality involve complex numbers. So you could have the imaginary number comes into play, but we're going to use a simplified version where the weights are just going to be plus one or minus one. Also, you may have seen, like if you've looked at any of this, you may have seen radical twos, stuff like this. We're going to be simplifying it down, that part down. We're just going to suppose that in a superposition, the weights are either going to be plus one or minus one in this talk, because that's all you need to really be able to understand the example that we're going to be looking at in the talk today. So the four key superposition states are basically going to be 0 and 1, and then the signs on each of them could either be a plus 1 or a minus 1. So you could have plus 0 plus 1, and we denote that kind of with this ket plus. So this would represent it's a superposition state it's essentially 50% 0 and 50% 1, and the signs are both plus 1, and the plus kind of indicates here that the signs are both plus 1. And then we have the state minus, which is when 0 sign is plus 1 and 1 sign is negative 1. We denote this with the ket minus. So the way that I'm going to think of this is here the signs agree, and here the signs disagree in the sense that they either are the same value or they're different values. So by the signs agree, I meant to say disagree for the pink one. Here the signs agree because they're both plus 1. They agree their signs are both plus 1. In the minus ket, the signs disagree. 0 is plus 1 and 1 is negative 1. If I continue on down here, you can see this next state is negative 1 on the 0 and negative 1 on the 1. So once again, the signs agree, but this time they view it as they're both negative 1. So actually, we write this state as it's negative plus, because again, plus is when they're both plus 1. And so it's like you can factor a negative 1 out of this. And it's like negative 1 times this plus. But the main thing I want us to remember in this talk is once again, the signs agree. They're both negative 1 in this case. And then the very last one, once again, the signs disagree. But in this case, 0 is the one that's negative 1, and 1 is the one that's plus 1. So the signs disagree. Okay. So these are the four main superposition states that we're going to be considering in this talk. And the key insight here is that, okay, the signs on the superposition can contain information. So we're actually going to be using the signs on the different states in the superposition to compute, to do some computation, and that the signs are going to reveal the information for us. So I want to talk, now that we've talked about these superposition states, I want to talk a little bit about um, about the way that you extract a value out of a qubit. So you extract a value out of a classical bit by just looking at it. If the switch is on, I can just see it's on, that's a 1. If the switch is off, I can just see it's off, that's a 0. Qubits are different. Um, so while you can think of it, like a classical bit as it's a switch, you can walk in, you can look at it, you can see what its state is just by looking at it. Qubits are not that way. They're like a box that you can't see inside. So if I've got a box that has one of these four superposition states inside of it, and you walk into the room and you look at it, you can say, "Oh, there's a box there. There's a qubit there. I can see there's a qubit there." But you have no way of knowing what's inside of the box. I know because I put it into the state. Like I have the power to be able to put it into one of these states. But if you come in and look at it, you won't be able to tell the difference between these four things. What you can do is you can perform an operation that's called measurement, which essentially, like, we're going to kind of use very simple. Um, we're going to abstract a lot of the details of how measurement works away in this talk, um, but for the purposes of this talk, you'll be able to kind of understand. So classical bits, you just look at it. Is the switch on or is it off? Okay. With qubits, you perform an operation called measurement. But so it will measurement reveals certain aspects of the state to us, but it also may alter or destroy the state as well. So it's like I get some information out of the state, but I might lose other parts of the information from the state. Okay. So the important capability for the purposes of this talk, if we know a qubit is in one of two specific superposition states, like whether the signs agree or disagree, like we talked about above, the quantum computer will be able to determine with certainty which one it is. Okay. So, for example, if we know that the state is either plus or minus, right? So plus is when the signs agree, minus is when the signs disagree. The quantum computer can tell me which one it is with certainty. Okay. However, if the state is negative plus or plus, we we won't get to determine that it's like which one it was. Like we won't be able to know if it was negative plus. We'll just learn plus. So in other words, the quantum computer can tell me if the signs agree. It can tell me if the signs disagree. But if the signs agree, it can't tell me if it's plus one or minus one minus one. It's just gonna say, hey, the signs agree. And same if they disagree. If it tells me it disagreed, it won't tell me if it's plus one or minus one plus one. I just get to know that the signs disagree. So that's the reason why I kind of categorize the superposition states according to whether or not they agree, because that's the information that the quantum computer can tell me. I'm saying that they do it with certainty. The reality is on an actual quantum computer, there is measurement error and readout error. It might screw it up, but um, the probability of that is fairly low. But for now, let's just assume with certainty, it'll let me know if the signs agree or if the signs disagree. And this measurement capability is the key to the quantum speed up that we're going to be presenting today. Okay, so far we talked about one qubit, right? The qubit can be 0 or 1, or it can be some combination of 0 or 1. And if it's some combination of 0 or 1, then we pay attention to the signs. Do the signs agree or do the signs disagree? So for multiple qubit states, suppose I have two qubits working together in a system. Okay. Then the way that we can get the state of the two qubit system is kind of like multiplying the states together. So if I've got qubit 1 is in the state 0 and qubit 2 is in the state 1, then you just simply write it as like the state 0 1. So essentially the first qubit is in state 0, the second qubit is in the state 1. So qubit 1, in this case, neither one is in a superposition state. And so then the final joint state also is not going to be in a superposition state. It's just 0 1. It's like representing the bit string 0 1 in a classical computer. But maybe my first qubit is in the state 0, my second qubit is in a superposition. Well, then in this case, what you end up doing it's kind of like you're multiplying these things together. then yeah, I can kind of distribute this through. So I end up getting a superposition of 0, 0 minus 0, 1. So we had a sign of plus 1 on this 0. So then when I drew, you have plus 1 and plus 1. So this is still going to be plus 1, 0, 0. But then this plus 1 times this minus 1, right, is going to give me this minus 0, 1. So the superposition state would basically be, it's kind of like it's 50% 0, 0, 50% 0, 1, and the signs disagree. Okay. Of course, they could both be in superposition states. Qubit 1 could be in a superposition state. Qubit 2 could be in a superposition state. And once again, you can kind of distribute these through to get the state for the two qubit system. I got to pay attention to the signs. So this is going to be plus 1 and plus 1. So I'm going to get a 0, 0. And then I'm going to get a 0 minus 1. So that's minus 0, 1. And then a 1, 0. And a minus 1, 1. So the two qubit system would basically be in this superposition state where it's kind of evenly likely to be 0, 0, 0, 1, 1, 0, or 1, 1. But then we've got this thing going on with the signs where the essentially if it ends in a 1, then the sign's negative 1, and otherwise it's positive 1. Okay. So um this is kind of the way that you can take individual qubits um and describe a joint state that describes like both of them at the same time. Okay. So now our superposition can have up to four different states inside of it here. So, okay. Well, it's all one state, but four different bit strings. The 0, 0, the 0, 1, the 1, 0, and the 1, 1. And they can all have signs. And again, right now we're assuming that the signs are only going to be plus 1 or minus 1. Okay. So now we're going to get into some quantum algorithms. So far we've just been describing like some properties of qubits, the different states they can have, and so on and so forth. And now I want to talk about like how do like quantum algorithms kind of end up looking like. So let's take a really simple example from classical computing. Suppose you want the logical and function. So you're given two qubits, and suppose that, so it's like 0 or 1. You can think of it, right? In the classical world, it's 0 or 1, and you're going to output 1 or true if both input bits are 1, 1, and otherwise you're going to put false. So your output false, sorry. So you want both of the inputs to be 1 to get a 1. Otherwise, you get a 0. Okay. So we all want to compute this on a classical computer. Okay. So now one of the properties of quantum mechanics tells us it implies that quantum algorithms must be reversible. And this is not a strength of quantum computing. This is it's in fact it's like an obstacle we have to overcome. Classical algorithms do not have to be reversible. Quantum algorithms do, and that hurts quantum. It's something you have to overcome in order to be able to obtain an advantage. So, what do I mean by reversible? I mean, if I tell you the function I run and I tell you the output, so like if it's like this, if it's f of x is equal to y, if I tell you the output and I tell you the function I just executed, you've got to be able to tell me what the input was. This is what it means to be reversible. If I tell you the output plus the function, you should be able to tell me what the input was. And of course, is not reversible. If the output is 0, if I tell you, hey, I ran the and function and I got an answer of 0, well, the input could have been any of these three things. It could have been 0, 0, 0, 1, or 1, 0, right? All of those give me an and calculation of 0. So and by itself is not a reversible function. Okay, so you can't determine the input from the output alone. Okay, that of course is not the end of the story, but unfortunately we have to. Well, it's not really unfortunate. I don't know. It's just like it's just one of the things. There's a way to overcome it. So that's what we'll talk about right now. reversible and that can be executed on a quantum computer. If I want a quantum computer to be able to compute and, how do I go about that? So the trick is you give it three qubits. You give the the quantum algorithm three qubits. There's going to be two qubits that represent the input values that I'm going to use to determine the truth value of and I'm going to color code those as green in the slides here. And there's going to be an output qubit, a third qubit that is basically going to be an output qubit, just its only role is to encode the answer. Okay, but so it's you could almost think of it as like you're passing it by reference if you're familiar with this concept. It's like I'm giving it the two inputs I want you to read to determine what the answer is, and I'm giving you a third memory location that you can use to encode the answer. Okay. So the way that the quantum computer is going to encode the answer, because this is because of the restriction that we have to be, our computation has to be reversible, is that if both input qubits are one, it is going to flip the output qubit. So rather than just like writing the answer of one to the output qubit, it's going to encode the answer by flipping the output qubit. So if the output qubit was in the state one, it will flip it to zero. And if it was in the state zero, you'll flip it to one. Okay, so you'll just basically negate it in some sense, right? And otherwise, you do nothing. And then it turns out this is reversible and it satisfies the conditions that the quantum computer, that a quantum algorithm needs to satisfy due, according to the laws of quantum mechanics, which again, if you go down the rabbit hole, you'll learn all about it. But for right now, it's just the laws of quantum mechanics tell us this is what we have to do. We have to do it reversibly, and here's a way. This is a way to do it reversibly. So you give me the input qubits and the output qubit, and then I'm gonna basically flip that output qubit if the truth value is one, and I'm gonna leave it alone if the evaluation was false. So here's kind of a truth table if I want to think about how the quantum algorithm will look like on any of the eight kind of non-superposition quantum states that we provide. So again, green is corresponding with the input qubits, and red is corresponding with the output qubit. So I'm going to look at the green input qubits to evaluate whether or not the AND function should be true or false. And if it's true, we will flip the red qubit, and if it's false, we will leave it alone. So for example, 0, 0, 0, the truth value of the two green zeros is 0, and therefore the output remains 0. So the input is always going to stay the same. You can see it in all eight of these. The green numbers to the left is the same as the green numbers to the right. The only thing that might change is the red number if the truth value is 1. So for example, like 1, 1, 0 and 1, 1, 1. These are the situations where the and evaluates to true. So if I give it 1, 1, 1, for example, if I give that as the input, then 1, 1 evaluates to true. That means, according to my pseudocode here, that I'm going to flip that output qubit. So this one will get flipped to a 0. And if I were to have given it 1, 1, 0, well, then it would have flipped that output qubit to a 1. So this is the way that this ends up working. The green qubits are always going to be the same, and the red qubit will change. Okay, according to whether or not the truth value is true or not. Okay, so now I claim this is reversible because, for example, suppose I tell you we ran and and got 1, 1, 0 as output. What is the input? What was the input? Well, you can, because the input qubits are part of the output, right? The two green input qubits are part of the output. So I can look and see what the green qubits are. In this case, they're 1, 1. I know that the logical and should have evaluated to true, which means that the output qubit was flipped. Since the output qubit resulted in a 0 and it was flipped, that implies that the input was 1, 1, 1. The green qubits are always the same in the input and the output, so it would be 1, 1. I know that and evaluated as true, therefore that red qubit had to have flipped. It ended up as a 0, so the input red was 1. Okay. Okay. So this is a reversible computation for this reason. All right. So like now if you end up essentially you get yeah, part of the trick is that well before we argued that the logical and was not reversible because if the answer was 0, then the input could have been any of these three things. Well, that's no longer an issue because those bits show up in the output. Like the you get the green bits in the output, so you know what it was. But then moreover, you still have to do this flipping thing in order to ensure it's reversible as well. So, um, yeah. Okay. So now here I've just described what how and works if it's not on a superposition state, where it's just like it's one of these bit strings and that's it. What if I apply and to a superposition state? Then what happens? So essentially, it gets a you could think of it as being applied linearly if you're trying to figure out what how this is going to apply. So if and gets applied to 0, 0, 1 minus 1, 1, 0. So now I've got a superposition state. Then you can think of it as you take the and for each individual thing here. So this is going to be equal to and of, I'm just going to keep the same color, minus, and again, the minus here comes from the minus there. So now I can just apply and to each of these individually, right? So this is going to end up becoming, so and applied to 0, 0, 1. In this case, 0 and 0 is false. So I'm not going to flip this. So this will still be 0, 0, 1, 0, 0, 1. And this 1, 1, 0, okay, the 1, 1 evaluates to true, which means I should have flipped that 0. So that's going to end up becoming a minus 1, 1, 1. So this is the way that you could think about what it is. It's like you just linearly apply the function to each of the individual components of your superposition state to figure out what the final state would be. So if I run and on this superposition state, I get that superposition state. But the important thing to remember here, this is only one evaluation of and. So even though I distributed the and through to help us communicate the way it works, The quantum computer does this in basically just one evaluation of and. This is not two. And moreover, like I used a small superposition to be able to write the answer quickly. But we could have provided a superposition of all of these different 8-bit strings. And you get the answer would be the superposition of all the outputs. So there would be 8 of them. But still, that's just one evaluation of and. Okay. This notion is called quantum parallelism. And this is a big aspect of how quantum computers have the chance to be able to provide an advantage over classical computers. You can essentially with one evaluation prepare your qubits in a state that can whose where their state is essentially a combination of all the answers all at once. So it sounds more exciting than it actually is because of the way measurement works, which again, I'm leaving some of these details out, but the reality is so you can prepare a state that has all of these answers inside of the state, but when you go to open the box to reveal some information to you, you only get partial of the state information given to you, and then you destroy the rest of it, right? So like we were saying, like you can't figure out if it's plus or negative plus. You just learn that the signs agree. So it's kind of similar. It's like, okay, it's not immediately clear how this is going to be useful to us compared to a classical computer. But there are situations in which it is, and that is where we are going right now. So is the problem that we actually want to show an advantage for, and that is Deutsch's algorithm. This is the kind of the one of the first problems that was demonstrated where a quantum computer can provide an advantage over a classical computer. So in some sense, like so this is a 1985 result, which is ancient for quantum computing. At the time, nobody knew anything about like, okay, is this actually going to potentially be useful or not? And it was kind of the first example where the classical computer doesn't do as well as the quantum computer. So you're given a black box function. So you're given a function f. F has a 1-bit input and a 1-bit output. So in other words, like f of 0 is either going to be 0 or 1, and f of 1 is either going to be 0 or 1. And so my function, it maps 0 to something and it maps 1 to something. And because there's two options for what 0 gets mapped to and two options for what 1 gets mapped to, there's kind of four different functions that you could do. Like they're either both 0, 0, 1, 1, 0, or 1, 1, right? So it's like the truth table. So there's four different functions that you could have. And my goal here is to actually determine if 0 and 1 have the same answer or if they have different answers. Is f of 0 equal to f of 1? Do they both have the same answer? Or do they have different answers? And so note the parallel with the signs that we've been talking about in the superposition states, where we were classifying the states based off of whether the signs agree or disagree. It's kind of a similar thing here. I'm trying to solve a problem where I'm trying to figure out if the function inputs agree on their answer or if they disagree on their answer. I don't care if they're both 0 or both 1. Like if they both get mapped to 0, they both get mapped to 1. I'm going to treat that as the same. I just want to know, do they agree? So the classical solution, you would have to there's kind of no way around it. I have to evaluate f of 0. So it's a black box in the sense that I don't know what the function is. Somebody else has it. You can think of ChatGPT as having it, right? So I asked ChatGPT, hey, what's f of 0? And it tells me 1. Okay. Then I ask it, okay, now what's f of 1? And it tells me 0. And then from there, I can say, okay, well, f of 0 was 1, f of 1 was 0. They disagree on their answers. Now I've been able to determine that the functions disagree. But I had to send two requests to ChatGPT to get the answer. I had to ask it what was the answer for f of 0, and I had to ask it what is the answer for f of 1. And then I figured out that they disagreed. Or I might figure out that they agree, depending on what ChatGPT picks to be the function. So the quantum computer, the thing is that it can figure this out with only one evaluation. And it uses superposition and the signs to be able to do this, so that I can I can ask ChatGPT to evaluate the function on a superposition state, and through quantum parallelism and some mathematical tricks, we'll be able to figure out whether or not the two functions agree on their answer. The two inputs, one function, sorry, the two inputs agree on their answer, or if they disagree on their answer. But again, just like in the superposition, I'm not going to learn if they agree, I'm not going to learn if they're both 0 or both 1. I will not be able to determine that. I'll just be able to determine that either they do agree or they disagree. Okay. So not a major improvement here. Um, But that's not the point. I'm just trying to get you to be able to, like, this is the first problem. This is a major win in 1985. The demonstration that quantum computers can do certain tasks faster than classical computers. And this ends up being still like in almost every quantum computing textbook, this is like the first example of quantum advantage um, that gets presented. So now I want us to be able to understand exactly like how does this work? Okay. So the quantum black box setup, all right? So again, suppose it's ChatGPT. It's gonna evaluate this oracle for us. So it has a mystery black box function. Okay. We send it a 2-qubit quantum state and we get back the answer after the function has been applied. So it's very similar to what we did with logical and. The 2-qubit state that I'm going to send it is what the first qubit is going to be green, that represents the input bit that it's supposed to be evaluating the function with. And I'm going to give it a red qubit, which is going to be the output qubit in which the Oracle ChatGPT is going to encode the answer. Okay. If f of input happens to be 1, it's going to flip the output qubit. And if f of the input qubit is 0, it's going to leave it alone. Just like with logical AND, except now there's only one input qubit instead of two. Okay. So again, ChatGPT picked the answer for f of 0 and f of 1. I don't know what that is. But once it has made up its mind of what that is, this is what it will do to my qubit state. If I give it a state where the input qubit happens to be evaluate to 1, the function evaluates it to 1, it will flip the output qubit, otherwise it leaves it alone. So this is a reversible computation. Everything is fine with that. Okay. Now the question is, what do I send it? So that's my goal is to prepare a quantum state to send to the Oracle to get the information encoded so that when it gets sent back to me, I can figure out what the answer is. So it's now on me as the algorithm designer to be able to figure out what state do I prepare so that I can figure out what the answer is. And I'm going to use superposition and sign tricks to be able to do this. Okay. So this is the standard algorithm. First, I'm just going to like show you what the way that it always appears in textbooks and things like this. Um, the answer that according to textbooks is that you prepare the state plus minus. You prepare the input qubit in the state plus. That's where the signs agree. And the output qubit, you prepare it in the state minus. It's where the signs disagree. +1 for the 0 and -1 for the 1. And in fact, we looked at this exact state earlier in this talk, and you end up getting this. So you get +0 0 -0 1 +1 0 -1 1. Basically, you get a negative sign whenever the red qubit is a 1, and you get a positive sign whenever the red qubit is a 0. Okay. So this is going to be the state that we prepare. So we send it to the oracle, and then once again, through through quantum parallelism, you could think of it as like the oracle gets applied to each of these four things kind of all at the same time. Okay, this is like a way we can think about the way that things are going on, which once again means that if the function according to the green input qubit is one, you're going to flip the red qubit, and if the green qubit function evaluates to zero, you're going to leave the red qubit alone. So what's that going to look like? Well, let's look at two different possible functions that ChatGPT could have picked for us. So suppose on the left, f of zero is zero, and f of one is one. And then on the right, we're going to suppose that they both evaluate to one. F of zero is one, and f of one is one. Okay. So, all right. So the way, okay. So I'm gonna write like the notation and the signs. I'm gonna leave those alone, and then we'll think about how these fill in. Because the only thing that's gonna happen is maybe the red bit flips, or maybe it doesn't. But the signs are gonna stay the same for now, right? So it's like okay. So I'll have a ket here minus a ket here plus a ket here minus a ket here. Okay. So it's like, okay, the answer to this is going to end up here. The answer to the second one is going to end up here. The answer to the third one is going to end up here. The answer to the fourth one's going to end up here. So in this case, whenever the input qubit is a zero, the function evaluates as zero, which means the red qubit is not going to change. So the two green zeros are on the left. Those two red qubits are going to stay the same. So we're going to have a 0, 0 for the two green qubits there. And then the red qubits are going to stay the same. They're going to be 0, 1 because the function evaluated it to zero. But for one, it's the exact opposite. Because the function evaluates to one, you're going to take whatever the red qubit used to be and you're going to flip it. So the two green qubits, input qubits on the right, are both going to be one. And then the red qubits are going to flip. So this zero is going to become a one now. And this one is going to become a zero. Okay. Now, the next thing I want us to notice is that in some sense, these two states just changed places because they both had an input of one. So their function evaluations are going to be the same. They're either both going to flip or they're both going to stay the same, right? When they both flip, this zero becomes a one, which is like the state on the right, and this one becomes a zero, which is like the state on the left. So in some sense, these two states kind of switch places. That's like the action of flipping both of them at the same time. The zero became the one, and the one became a zero. So it's almost like the states changed places. And that ends up mattering because of the signs, right? So it's like we used to have a plus one zero and a minus one one, but now we have a plus one one and a minus one zero. So it's like they change places. So now what I'm going to do is write them back in kind of the bit string order, like if you think of them as binary numbers. But then when I rewrite the terms, I'm going to move the signs with them, right? Because after all, 1 1 is now positive, and the 1 0 is now negative. So I'm going to have this. Yeah, so here, let's write so this, I'm going to have a 0, a 0, a 1, a 1. And then in the reds, I'm going to have, again, I'm going to write in bit string order 0, 1, 0, 1. Just like in the order that I wrote them before. But now I'm going to figure out be careful with the signs. So we're going to have all these cats. And the question is, what are the signs? Well, this one stays the same. So the 0, 0, 0, 1, it's this sign's negative, right? This 1, 0, its sign is now negative, right? And this 1, 1, its sign is now positive. So like when I think about what my input was to jumping to here, you can kind of think of it as if these two states swapped signs. Like that's not what happened really. It's like the two states swapped places and the signs happened to be the opposite of each other, so it's like they exchanged signs. So intuitively we could think of it this way, right? If the function evaluates to one, both of the red qubits are going to flip, but that's effectively going to swap the signs. So this plus and this minus got swapped. Okay. Now let's do it on the right side when the function is both one. So in this case, so right now I'm going to leave the signs alone. And I'm just going to think about how all of these things end up flipping. So the input qubits are always going to be the same. This is a 0, 0, and a 1, 1. But in this case, since both functions evaluate to one, like in all scenarios, you're going to flip the bit. This red zero is going to change to a one. This red one's going to change to a zero. This red zero is going to change to a one. This red one is going to change to a zero. Okay. So when I do this, like this one maps to this one maps to this one maps to this one maps to this. Again, it's the same. Like this 0, 0 and this 0, 1 kind of change places, and this 1, 0 and this 1, 1 they change places, but the signs didn't move. So changing the places of the states while keeping the signs the same is effectively the same thing as leaving the states the same but changing the states, which once again, sorry, changing the signs, leaving the states the same but changing the signs. So now I'm going to go back and rewrite the terms in bit string order. So 0, 0, 1, 1, and then 0, 1, 0, 1. But now I'm going to pay attention to the signs. What's 0, 0? 0, 0 sign is negative. 0, 1 sign is positive. 1, 0 sign is negative, and 1, 1 sign is positive. So this is the part to try to maybe pause and go back and make sure this syncs. If the function evaluates to 0, the signs and the superposition stay the same. If the function evaluates to 1, the signs in the superposition flip. That's the way that I would encourage you to think of it. Okay. So when they're both 1, they both agreed to flip the signs. When one was 1 and the other one was 0, they disagreed. One of them flipped and the other one stayed the same. Okay. Now I want to factor this back out into like individual qubit states. So we can, so long as they're not entangled, you can factor the states back out, which we're not really talking entanglement here, but right now I can factor these states back out. So we can see on the red qubit here. Yeah, so here I'm just I feel like with this one we have to kind of yeah, let me write it down and then I can try to give some intuition. This is gonna be 0, -1. The red qubit will be 0, -1. Um, because you could see that like when the reds, so for a fixed input, the 0 and the 1 disagree on the signs. The 0 and the 1 disagree on the signs. So that kind of forces it when you're factoring the state back out to leave this as 0, -1. Then on the left side, the green qubit, okay, like is it going to be Basically, I want to figure out is it 0 plus 1 or 0 minus 1 or is it -0 minus 1 or whatever? Like, what is this superposition? So it's going to be in this case, I can see, okay, so 0 0, so the zero's got to be positive. So this is going to be a positive one, positive zero. And then here, when the green is 1, this one's positive, but I see the sign should end up becoming negative. So it's going to become a -1 minus the state 1. So the input qubit is in the state 0 minus 1, and the output qubit is in the state 0 minus 1, which this is the state minus minus because the signs disagree. The green qubit is minus, the red qubit is minus. Now, what is it on the other side? I want to factor these out. Okay, so you're going to have an input qubit, you're going to have an output qubit. Once again, the output qubit needs to be the state minus because when you fix the green and you change the red, you flip the sides. So the red qubit is going to be 0 minus 1. Turns out this is always going to be the case no matter what the F is. 0 minus 1. And now here I can see, okay, the green actually needs to be minus in the output because 0 0 should end up having a -1 sign. So I need the green 0 to be -0. And then for 1, okay, once again, this is a -1 0 and this one's +1, so this one also needs to be minus. So it's going to be -0 minus 1. So you can see here the green superposition, the signs agree. They're both -1. They both are -1. So this ends up becoming the state. I'm going to write it as minus plus minus. Oops. So the minus sign out here is because it's not plus, because if it was plus, this would be plus plus, right? But again, the important thing here is that the signs on the green qubit both agree. So on the left, when the two functions evaluate to different answers, the input qubit is in the state minus. When they have the same answer, the input qubit is in the state 1. Sorry, it's in the state plus. It's in the state plus. And that ends up becoming how the algorithm works. The quantum computer can let me know with certainty whether or not this input qubit is in the state minus or plus. Does the input qubit, does the signs agree or disagree? And then that reveals to me the answer. If they disagree, or sorry, if the signs disagree in the superposition, which means it tells me it's minus, then that means one of them flipped and the other one didn't. But if I check out the input qubit and I see the state plus, it means that either they both flipped or neither one flipped. And yeah. And the quantum computer can tell me which one it is. So by preparing this input state, sending it to my Oracle, ChatGPT, it'll evaluate this stuff and send it back to me. So at that point in time, I get my qubit state sent back to me. It's inside of a box. It's going to be it's going to be the exact state. I don't know what it is, but I can measure the qubits, really the first qubit, and I can figure out if the answer is plus or if the answer is minus, and it will tell me that. And depending on that answer, I can figure out if the function f, if the two inputs agree on their answer or if they disagree. Okay. So now the question is, okay, so this is the way that it's oftentimes presented in textbooks. Like you just are like told this is what it is, and it's almost left as an exercise to the reader to be able to verify why why the math is what it is, which to me is not a very satisfying answer. I like to have some more intuition how to think about things. So one of the ways I like to try to do that is what if I change stuff? What if I take part of the problem and I change it slightly and then ask, does it still work or does it not work? Because whatever the answer to that is can help strengthen the intuition for like, why did this actually work the way it's presented? So let's check it out. What if I prepare a different state for the oracle? Like what happens? Okay, this slide says what I've already said. Okay. And this slide also says what I've said. Okay, so I'm gonna go through this. Yeah. What if we prepare plus plus? So this is what I want to talk about now. What if we prepare the state plus plus? So remember, like effectively, like what happens depending on what the function does is you're swapping the signs between the two states. So like either like these two things, their signs are going to flip or they're not. And here they're either going to flip or they're not. But the problem is all the signs are plus one in this state. If you prepare the state plus plus, all the signs are plus one. So if I swap them, what did you just swap? You just swapped two plus ones. You can't tell the difference, right? Like did you swap them or not? You don't know. Either way, they're plus one plus one. So hopefully it's kind of clear that this just definitely does not work, right? Like you're not going to be able to get any sort of difference here, right? So you need to have both signs plus one and minus one represented inside of your state if you're going to have a chance of being able to detect something. So clearly plus plus just doesn't work for this one. Okay. So what about minus plus? If I do minus plus, this gives me two plus ones and two minus ones. I got plus 0, 0, plus 1, 1, minus 1, 0, minus 1, 1. Okay, what happens here? The problem is the two plus ones are both tied to the input bit being 0, which means if you swap the signs or not, you're not going to see a change in the signs for these two things, right? If I swap, you're swapping the plus ones again. The two minus signs go on when the input bit is 1. If you swap them, you're going to swap the two negative ones. And so it's you still run into the situation where whether you swapped or not doesn't change the state. You're still going to have negative ones in both places. Or if the green bit is 0, you're going to have plus ones in both places. So swapping the signs doesn't do anything. Does not change the state at all. So if it doesn't change the state at all, certainly you're not going to get any useful information out of that. So it turns out that minus plus also doesn't work, right? So hopefully now we can be zoomed in on the fact that in order for this to have a chance of working, the sign, like these two signs have to be different, and these two signs have to be different so that you have a chance that when you swap, you're actually swapping different values. And it turns out that in order to have that happen, the red qubit has to be prepared in the state minus. That is what creates that. Okay? But what about the input qubit? So what we did before was plus minus. What about minus minus? Like so what happens if I change the input qubit to being in the state minus? Now, these will be the signs, right? It'll be plus 0, 0, minus 0, 1. Okay, so those signs are different for that green qubit. And then minus 1, 0, plus 1, 1. Once again, these two signs also are different. They're kind of reversed from the zero case, plus 1, minus 1. Now we have minus 1, plus 1. But actually, it works, right? Because in this situation, if you evaluate the oracle and you flip, you're going to be flipping a minus 1 and a plus 1. You have the different signs assigned to the same input qubit so that when you flip them, you are actually changing the state. Now the state will be the same or different depending on the function evaluation and the way the oracle works here. Okay. So flipping the output will create a detectable change in the quantum state. So that's good. However, now the final way that we take our measurement result and interpret that as to whether or not the functions have the same answer or not is reversed. Previously, if we saw that it was a plus, the input qubit resulted in the state plus, we said that the states agree. But actually now it's going to mean that they disagree. So I think the intuition here is like the input started in minus. So if you just don't do anything, like if they both evaluate to zero, which means you don't do anything at all to the state, then you'll still be in the state minus afterwards, right? So like if they both do the same thing, you'll get back out the same input qubit state that we started with. But if one of them flips and the other one stays the same, then it will go to the opposite sign. So now plus at the end, since we started with minus, if we get a plus, that means that they did different things, which means that the functions evaluated to different answers. But if we start with the minus before and you end up with the minus after, that means that they both did the same thing. They either both flipped or they both stayed the same, in which case we end up getting the minus. Okay, so to conclude, the output qubit must be prepared in the state minus for this to work. If you prepare the output qubit in plus, it does not work. You won't be able to detect the change. The flexible choice, the input qubit, it can be in either one of the two superposition states. It can be in the state plus or minus. Pick your favorite way to go about it. Again, the textbooks will always tell you plus, but you can use minus. Okay. And by the textbooks, I mean the textbooks I've read. I'm not trying to imply that I've read everything. This may not be new information. I'm not trying to claim that anything I'm presenting here is new. But I do hope it's useful to be able to think about it. You cannot change the output qubit from the original Deutsch's algorithm. The input qubit you can change. It doesn't make a difference, but you have to know what you prepared it in so that you know how to interpret the final measurement result. So the quantum advantage is that the classical, again, needs to evaluate f of 0 and f of 1 and compare the results. The quantum just needs to evaluate it once by carefully picking a superposition. And then I look at my input qubit to reveal if it was a plus or a minus, and then I can figure out if the function was, if the function inputs agreed or if they disagreed. Okay. Right. So hopefully you're still with me. I just found it so frustrating to go through a ton of background before I ever got to see an advantage of quantum superposition, or sorry, quantum advantage. You see superposition right away, but how is it useful is not seen until after you've gathered a lot of background. So I've hid a lot of things from you here. I've hid the fact that these states are vectors. I've hid the fact that these quantum function evaluations can be represented as matrices. I've hid that all these signs are actually complex numbers and are not actually plus one, minus one. They're different things. Okay. I've hid a lot to try to get us here, but I hope that this can encourage you that, hey, this is kind of cool. And maybe it is worth it to go down the rabbit hole. So if you want to go down the rabbit hole, if you are a computer scientist or a mathematician or somebody who doesn't have quantum mechanics, and you want to be able to learn it the right way from a linear algebra foundation without having to learn all the quantum mechanics in advance. We'll learn the quantum mechanics along the way. UT San Antonio is a great place to do it. We're doing practical quantum computing, lots of programming, hybrid quantum classical. We're trying to figure out how we're going to be able to take this emerging technology and figure out how to do some really cool things in a practical way with it. And yeah, so anyway, little hoorah pitch for our program. But thanks everyone. Please let me know if you have any questions and if there's a way I could improve it. I really would like to be able to get more people who are like me involved as painfully as painless as possible because it can be a painful process if not done the right way. So, um, thank you.